Hello everyone, and welcome to this new series of tutorials about Fantasia. And in this series, we will be covering Bayesian networks to support AI systems in Unreal. In this series, I will show you how to handle probabilistic input and how to combine it with the AI systems of Unreal to take decisions at runtime that take into account probabilistic distributions. Specifically, we will be considering the case of Bayesian networks, which are now integrated in Fantasia. So first of all, what is a Bayesian network? Bayesian networks are probabilistic graphical models that model causal relationships between random variables describing different aspects of the problem at hand. They consider both a priori probabilities and evidence collected at runtime to support inference. So this means that we can input in the Bayesian network both what we know before observing anything in the problem at hand in the session that we're managing. We can also collect evidence about the random variables present in the Bayesian networks, for example, by asking questions or by observing things. To support inference or reasoning, we can derive deductions, probabilistic deductions from our observations and from what we know a priori beforehand. Bayesian networks are very useful to support decision systems, especially when the input is noisy, like for example when we're designing conversational systems. In Fantasia, we use the aGrUM library. I will be putting a link in the description if you want to know more about aGrUM. In general, aGrUM stands for a graphical universal modeler, and it's a C++ library to manage probabilistic graphical models. It is very flexible and is a powerful implementation of Bayesian networks among other types of graphical models. It supports inference and parameter learning, so that is why we chose to integrate it in Fantasia. Bayesian networks are structured like this. We have nodes that represent, for example, causes, and these nodes are connected by arcs with other nodes representing the effects. All of these nodes will contain probability distributions describing how probable is the cause, for example, and how probable become the effects depending on what we know about the nodes that cause them. So we can, for example, try to observe how probable a cause is in order to predict how probable the effects of that cause are. Effects can have multiple causes, so a single effect can have multiple parents, and all these parents will be influencing the probability of observing the effect. Here's a classic example of Bayesian networks describing how probable it is for the grass to be wet. We have a first random variable, a node, describing the probability that the weather is cloudy. We have 50-50. We have two possible values for the sky to be cloudy or not. 0 is not cloudy, 1 is cloudy. And we have a 50-50 probability of the sky being cloudy. The sky being cloudy influences both the sprinkler being on or the rain to be present. Since there is a causal relationship between the sky being cloudy and the sprinkler and the rain being present or not, the sprinkler being on or off and the rain to be present or not, the probability of the sprinkler to be on and off depends on the sky to be cloudy or not. So for example, if the sky is not cloudy, then we have a 50-50 probability of the sprinkler being on or off. But if the sky is cloudy, then the probability of the sprinkler to be off is 90%, and we have a 10% of probability for the sprinkler to be on. Same goes for the rain. If it is not cloudy, then we have a 80-20 probability distribution for the rain to be not present or present, and 20-80 for the opposite case. The grass being wet is influenced by the sprinkler being on and the rain being present. So we have all the possible combinations of the values for the rain and the sprinkler influencing what happens to the grass. So the grass will not be wet if the sprinkler is off and there is no rain, and for certain it will not be wet, it will be dry. For all the other cases, we see different distributions depending on all the possible combinations of the values that the parent distributions can assume. So this is a Bayesian network. It is describing causal relationships between different aspects of the problem of the wet being grass, and it supports us in deciding at runtime whether it is most probable for the grass to be wet or not. Let's see how this works. After assembling our network, we can already make inference about the probability for each node to assume a value or the other. So for example, here we have a 50-50 probability of the sky being cloudy, 50-50 for the rain to be present, 70-30 for the sprinkler to be on, and a 64-71% probability for the grass to be wet. We can make inference based on a priori probabilities only before doing anything else. What we can do while we are interacting, for example, is to collect evidence about these nodes, to actually observe what is going on. Suppose we observe that the sprinkler is on and that the sky is not cloudy. We can apply evidences on these two nodes, C and S, stating clearly with hard evidence in this case that the sky is not cloudy and the sprinkler is on. All the distributions about which we do not have evidence are updated accordingly. We don't have to consider hard evidences only. We can also apply soft evidences to nodes, so modify the distributions, and in this case too, we can make an inference and update the probability distributions of the nodes for which we do not have collected evidence. This means we can use probabilistic information in the graphical model to handle our AI, to make the AI take decisions about, for example, what to ask or what stance to take about specific problems like the probability of the grass being wet. A very useful information that we can get from the nodes is the uncertainty that we have about the nodes. This is called entropy. Entropy is a measure of uncertainty, and it will be zero when we are absolutely certain about something. We will have a value higher than zero when the probability distribution is more uncertain. When we have a uniform distribution, we have the maximum entropy value because everything has the same probability to happen, so we have maximum uncertainty. Let's see how it works in a simple example. So let's take this variant of the Bayesian network that we are considering. For each node, we can compute its entropy and take a value. So the entropy is marked as h, and the name of the variable is the parameter of this h function. For each node, we get a number. So if we suppose that we want to take a stance about the probability of the grass being wet, we want to reduce the entropy on the W variable. What we can do about it if we don't want to ask directly if the grass is wet or not? We can collect evidence about the causes of the grass being wet, in this case by asking questions. Which question to ask? In this very simple example, we will take a very elementary strategy and we will systematically investigate the nodes that influence the node of interest that have the highest entropy. So in this case, we will ask if it's raining because the value of the entropy for the R node is higher than all the other nodes causing W. Suppose we want to take a stance only when we are very sure about the distribution of W, and let's assume that we want to take a stance when the entropy of the W node goes below 0.1, which is an extreme value. So if we collect evidence about R, then we can ask if it is raining, and we can get an answer. In this case, we got a yes as an answer. So we have evidence about the fact that it is raining. So the entropy of the node representing raining goes to 0 because we are absolutely sure that it's raining, and all the other probabilities are modified accordingly. So as you can see, the entropy of W was reduced. Still, it is not reduced enough. So by using the same procedure from before, now we have two possible nodes from which we can choose, and this one has the highest entropy. So the next thing that we're going to do is to ask whether the sprinkler is on. If we get a yes again, then the entropy of this node goes to 0 again, and the entropy of W goes below our threshold. So we are very sure that the grass will be wet, and we don't need to ask anything about the sky being cloudy or not. We will use this very simple strategy to have our conversational agent decide whether he thinks that the grass is wet or not in Unreal, and I will show you how to import the Bayesian network that we can design with aGrUM in Unreal and how we can query it by using blueprints in order to take decisions.